In this diagram, the line segment AC is a chord. With O being the center of the circle and OA and OC being the radius, the angle formed AOC is called the angle at the center. The points A and C split the circumference into a major and a minor arc. The point B is on the major arc. Connecting AB and BC directly results in them being two chords. The angle formed between them, that is the angle ABC, is called the angle at the circumference or the inscribed angle. The chord AC subtends the angle ABC. What that means is that the chord AC holds on to or forms the base on which the angle ABC is formed. The first property states that this angle at the center is twice, that is double the angle at the circumference. In this accurate construction, the angle at the center is 100 degrees, and as per the first property, the angle at the circumference is half, that is 50 degrees. Watch what happens to the angle at the circumference when we move the point B on the major arc. The point B can be moved to any point on the major arc, and the angle at the circumference, that is the angle ABC, will always be half the angle at the center. And the angle at the center does not change, thus the angle at the circumference remains the same. To further investigate, we can move the points A and C such that the length of the chord AC changes, thereby changing both the angles. At any instant, the angle at the circumference is half that at the center. With the final changes made, the new angle at the center is 50 degrees, and as per the first property, the angle at the circumference is half, that is 25 degrees. Moving the point B again on the major arc results in no changes, thus validating the first property, which states that the angle at the center is twice the angle at the circumference. The second property is an extension of the first. It states that the angles in the same segment are equal. The chord AC splits the circle into two segments, the major segment and the minor segment. The angles at the circumference at B, D, and E are subtended by the same chord AC and are in the same segment, which is the major segment. We had investigated a similar situation earlier in the first property by moving B on the major arc towards D and E, resulting in the same angle at the circumference, and this is what is implied by this property. Moving B, D, and E on the major arc moves the angles within the major segment, and the second property states that they are equal. To further validate, we can change the length of the chord AC and observe that the angles at the circumference in the same segment are always equal as per the second property and are half the angle at the center as per the first property. The third property states that the angle in the semicircle is a right angle, that is 90 degrees. This can be easily proven using the same construction and logic of the first property. The points A and C are moved until the line segment AC forms a straight line with the center of the circle O on it. In other words, AOC becomes the diameter, which we have learnt before as the largest possible chord, and the diameter splits the circle into two halves called semicircles. In this situation, the angle AOC is 180 degrees on both sides. In other words, the angle at the center is 180 degrees. Applying the first property results in the angle at the circumference, which is now inside a semicircle, being half, thus 90 degrees. Moving the point B anywhere on the circumference maintains the angle at 90 degrees due to the symmetrical properties of the circle. Therefore, the angle in a semicircle subtended by the diameter is 90 degrees. A cyclic quadrilateral is a four-sided polygon whose vertices lie on the circumference of a circle. In the construction shown, the points A, B, C and D are the vertices of a four-sided polygon ABCD and lie on the circumference of the circle. The fourth property states that the opposite angles in a cyclic quadrilateral are supplementary, that is, they add up to 180 degrees. Consider the angle at B. The angle opposite to it is the angle at D. As per the fourth property, adding these two angles will give 180 degrees, and it does. Now consider the angle at A. Opposite angle is the angle at C, and adding them up will give 180 degrees as well. To investigate further, we move the points A and B, which changes the shape of the cyclic quadrilateral. And we can see that at any instant, the two opposite angle pairs add up to 180 degrees. We have looked at the tangent radius system in the previous lesson. Here, the fifth property states that the angle between the radius and the tangent is 90 degrees. This implies that the radius drawn to the point where the tangent touches the circle will always be perpendicular, that is 90 degrees to the tangent.